Okay, so welcome to this webinar series, the first of a few webinars that we will be doing in the coming months, and also uploading these webinars to our YouTube channel. This particular webinar, we're going to be covering how to safely and efficiently commission and maintain 1000 volt and 1500 volt PV arrays. I hope you get something from this session. Please feel free to ask us questions, which I'll be covering at the end of the session. If you are watching this on YouTube, you can of course email us or contact us at sales@seaward-groupusa.com. Also messaging us on YouTube is effective. We will respond. We're also available on Facebook, on LinkedIn, on Twitter, which you can find us obviously if you Google, and the links will be in the description below. But now let's get started on today's webinar. My name is Michael Middlemast. I'm the Business Development Manager for North America here at Seaward Group. I've been in the solar industry around about 10 years, so over a decade. I began my life specifying residential systems. I moved into more complicated systems, commercial systems, factory, agricultural systems. I then went on to run a wholesale business where we designed and put together kits for local installers in the United Kingdom. From there I worked with a racking system manufacturer, and from there I worked for an inverter system manufacturer, and then finally that led me to my role here at Seaward, and I've been with Seaward now for around about 18 months, 2 years. And during that time I've had a lot of experience on site with PV test equipment, and I have a lot of experience with the issues that are faced on site and how we could approach the measured data that we receive from our testers and how we actually make sense of that data. So that's what the webinar will cover today, and I hope you find use of it. And again, if you have any questions, the Q&A session will be at the end of the webinar. So first of all, I just have a little disclaimer. I need to read this out to you, so please do pay attention to this one and refer back to it if you do have any kind of legal questions with regard to the training. This presentation cannot be considered a replacement for any of the standards I reference, and reasonable care has been taken to ensure the accuracy of the information, of the reference figures, of the data that's been taken from these standards. We don't take any responsibility for any error or omissions within the presentation or any misinterpretation by you, the user. So for any clarification, please do get in touch with us. No part of the presentation is deemed a contract or form of training unless otherwise stated. And persons performing any electrical tests described within this presentation, you must be fully competent to do so, and we can't take any responsibility for any accidents directly or indirectly that may happen as a result of this training. The safety of our operators and our users is absolute paramount above everything else, so please do take care of yourself. Okay, that's the disclaimer out of the way. Let's get into the good stuff. So a little bit about Seaward Group USA. We're based here in Tampa, Florida, serving North America, but we also serve international markets. We also have an office in the United Kingdom, Seaward Electronic Limited, where we service the United Kingdom, Europe and Asia, and we pretty much service solar installers and operators all around the world. We have a high level of technical support, so you can expect webinars like this quite often from us. We give all of our users one-to-one training if they need it, either on-site or via this live training studio. And we have fast delivery and competitive prices. So all of this training and support would be nothing if we can't get our instruments to you as quickly as you need them. So that is available from us also. We offer several test solutions, and throughout the training program which I'm about to give to you, I will be referencing these particular instruments. First of all, we have our PV150. This will give you open circuit voltage, short circuit current, insulation resistance, earth continuity. It also comes with an amp clamp, which is very useful, and attaches to an irradiance meter. Our PV210 is everything the PV150 does, but it also has IV curve tracing. It's a very portable handheld instrument, and it can take measurements very quickly. We are also an authorized distribution partner of Sol Metric products, so we can offer you the PVA 1000S at very reasonable prices with, again, high level of technical support. There are also 1500 volt solutions available, and 1500 volts, which we will go into in the webinar, is becoming more and more prevalent in our industry. So we've created a solution of our own to help you very quickly and efficiently check the performance of these arrays. So the Seaward Solar Utility Pro String Checker is rated at 1500 volts, 40 amps. So it's incredibly useful for testing multiple strings in parallel, particularly when we have multiple strings going into a single fuse in the combiner box, which we're also going to cover in the presentation. And this is available for pre-order now, for delivery in November. Now, if you're watching on YouTube and it is November, then get in contact and you can buy it now. Similarly with the Solmetric instrument, which again, we are an official distribution partner with Solmetric. They have a 1500 volt IV curve tracer coming in December, and that is also available for pre-order. It's the most accurate IV curve tracer available on the market. It's rated at 30 amps, so it really is a very good instrument to be using out there in the field. A combination of both of these I find is very good. Something to do the pre-commissioning tests would be the Solar Utility Pro, and then if you need IV curve tracing, particularly on a very high percentage of a solar farm, and then I would use the Solmetric PVA 1500. So, as I said earlier in the disclaimer, the main concern that we have on a PV site is safety, and safety is absolutely paramount. We need to make sure that our users are operating safely, they understand what kind of voltages and amperages in front of them, and what damage could be done to them, not only themselves, but those around them, their equipment, and we really need to focus very heavily on safety. With this in mind, there are some very basic measures you can take towards electrical safety, and if you're used to dealing with AC systems, maybe in commercial buildings or in residential homes, DC is slightly different, so you should take extra care. It can arc a lot more. So I would suggest rubber insulated gloves as your first line of defense, and consider covering these with leather gloves. This will give you an initial protection with your hands where you're actually inside the combiner box or at the solar panels themselves. And also you should wear the appropriate personal protection equipment with regard to arc flash protection, helmets. When you're walking around a solar farm, there's lots of steel pointing out everywhere, or aluminium, which could poke you in the eye. So it's always good to have eye protection as well. PV systems can operate at a high of 1500 volts. So arc flash requirements are very much a growing concern. And unfortunately, not all systems are clearly labeled. So this point is that if you're on a new system, you probably know what you're dealing with. But if you're going back to a site to do some maintenance work, you might actually know what the string length is, or what the history of the solar farm is, particularly if it's not very well labeled. So it's very, very important just to look at the panels, count the number of modules in the string, and try to understand what you're dealing with before you connect your tester. And we're going to cover that a little bit later on. Finally, before you arrive on site, we should really perform an on-site evaluation with regard to safety. A lot of new construction of solar farms, of course, they have health and safety officers on site. All the risk assessments have been done. But if you're a subcontractor and you've been asked to go to a legacy site and there's been no on-site evaluation of health and safety done, you should really request that, because your health could be at risk, particularly if, as I mentioned earlier, if there is no idea of what the string configuration is and the level of electricity that you're dealing with. Finally, on this point, if you get to site and you have brought your personal protection equipment, if you feel it's not enough for the system that you're testing with, just stop testing and go away, get the correct PPE and come back. Don't be afraid to say, I'm sorry, I can't work on this site. I don't have the correct personal protection equipment. It's always a very good idea to isolate the AC side of the array. When we're testing the panels, we don't need any of that. We don't need any connection to the grid. So if you possibly can, always isolate the AC side. This can cause many problems, particularly if we have, if we're testing in a string inverter where it's directly connected in. Just be sure to isolate the AC side whenever you're working with the DC side. So I thought before we got into really discussing how and why and when we should test, I thought it might be good to bring to the attention the differences between 1000V and 1500V systems. Because this is so new, not a lot of people have an idea of why we're even using 1500V. And if you do, that's great, but there might be some in the audience that don't. So I'd like to cover a few of the points and why I think we're moving more towards 1500V systems. Well, obviously, if we have higher voltage strings, this means we have a lower current. So this results in a reduction of power loss. Okay, so that means we're generating more power from longer strings. With 50% longer strings at 1500V than 1000V, this means we have a lot of less wiring. There's a less cable, fewer connections, fewer combiners are needed, and overall that really drives down the balance of system costs. So you can save a lot of money per kilowatt peak, and indeed per megawatt peak with a 1500V system. And if we have fewer but larger inverters, that means we're also going to save money because the components of the inverters are housed within a similar space as the 1000V systems. So again, we're saving cash not only on the connections and the wiring, the combiner boxes, but also at the DC to AC inverter end. And overall, if we have less materials on site to install, this also lowers the labor cost. So we can put in more solar quicker, or we can put in the same amount of solar for a lower cost. So really, the industry moving to 1500V is a very good thing. But I guess me as a test instrument manufacturer and supplier, we've been trying to play catch up. And that's why we've introduced our Solar Utility Pro, and also that's why Solmetric have their 1500 curve tracer. So it's almost as if us in the testing industry, we're finally getting up to speed with where the industry has been with 1500V systems. So that all sounds very good, but there are some drawbacks and there are some things we should watch out for. Lower current strings, they're often put in parallel. Okay, so what this does is this multiplies the short circuit current. So if we have an 8 amp string and we put two of those in parallel, basic electronics tells us that that's 16 amps. And we have multiple strings going into a single fuse in the combiner box. Now, this means we can buy less fuses. All right, they're bigger, but we have to buy fewer of them. And also we have fewer combiner boxes again. But what that means is in that single fuse, there could be a lot more current than you're ever used to. So this is why with the Solar Utility Pro, we went for a really high rating of 40 amps. So we're at 1500V, 40 amps. So you're at a very good position where you've got a lot of headroom that if you test a 30 amp fuse, you've still got a lot of capacity there within the instrument. I mentioned on the previous slide that if we have fewer inverters, we're lowering the cost. But overall, we're putting our eggs in fewer baskets. So that means we're increasing the losses during our downtime. So if one of the bigger inverter goes down rather than one of our single little inverters, then we've lost the whole generation. So that is a consideration, particularly for inverter manufacturers, to increase their reliability. Also, higher voltage strings are more susceptible to PID, a potential induced degradation. Just very briefly on this concept, this is when the voltage, the power within the solar panel is trying to escape into the metal mounting frame, the frame of the panel, and also to the back sheet. And this degrades the silicone over time, and we call this potential induced degradation. So, as an industry, we really must become more PID vigilant and look out more for PID, particularly on 1500V systems that have been installed for a longer period. So right now, it might not be so apparent, but during the life cycle of that system, PID, I think, is going to be very much more apparent than in 1000V systems. We can detect PID with electroluminescence testing. In the past, PID has been tested by various ways, and EL testing has certainly been the most effective. But normally the only method of testing EL is on a night, where we energize the PV system and then we use an electroluminescence camera to take an image and determine where the PID is. We have access to a solution called DaySci. You're able to detect PID during the day with EL while the modules are in situ, so no need to remove the modules from the racking. It's a very good tool. It is slightly expensive, but in comparison to other on-site EL testers, it is very, very effective. So if you have any questions or would like to know more about the DaySci system, I won't be covering it in this presentation, but please do get in touch. So those were the differences between 1000 volt and 1500 volt systems. And what I like to say to our users is, before you even connect your instrument, let's do some pre-testing preparation. So the very first thing we should do is the visual inspection. So this may sound like a bit of a given, but if you're going to test, we should take a look at what we're testing first. And you would be surprised how many people straight away disconnect panels, connect the instrument, test, without even looking at what they're testing. So particularly if you're working at the combiner box, you could be testing a string that's 200 feet or even more down at the bottom of the table. So it's always good just to have a walk up and down the table to see if you can see any problems with the front of the modules first of all. So we're looking for cracks, we're looking for spotted shading, which could be bird droppings or leaves, and we just want to maybe clean that off and just make sure that we're going to be testing a nice clean array, which I will also cover shortly. This image that you're seeing here, this was a solar farm I was on in Dubai. It was a 260 megawatt farm, and as you can imagine, this is in the middle of the desert, and what was happening was the sand was covering the panels, and they were having to clean the whole solar farm every 9 to 10 days. So very, very trying, very hard to keep the generation up. But what was happening was, where the cleaning JCBs were coming through, which I have an image of, which I didn't put in, apologies. But as the machine was coming through, and you can actually see the track down the bottom of the panels, and that was kicking up stones and smashing individual panels. So this was a real problem and something we should be careful of, and something we should look out for during our visual inspection. So once we've had a look at the front of the array, I would then take the walk back along the back side of the array. And at this point, what we want to look at is the cabling in particular, because this is where the major problems I find, and the majority of the problems I find on solar PV farms, particularly the MC4 connections. If they're not made correctly, or if there is dust in the MC4 connections when they're made, this can cause arc faults inside of the connection, and you can see that on the image on the top left hand of the screen. Also, if the cables are like this, as you can see in this picture here on the right, if the cables are like this means when it rains, the water is going to run down the cables and go into the MC4 connections. And what will happen there, we'll get an insulation fault, and we could potentially have arc faults if it's affecting the connection. And what will happen is, and I've seen this also in the field, is we've had users go out and test in the morning after it's been raining and it's been very wet, and that moisture is inside the connection. They run a test with their instrument and they get a low insulation resistance. Then they go back later in the day and retest, and the insulation resistance is fine. We get a good level of insulation resistance. What's happening there is the moisture in the cables is actually drying during the day. So this is a very big problem. So while you're doing your visual inspection, if you see any cables hanging down, just lift them up, maybe cable tie them and secure them properly. They shouldn't be looking like this. You'll notice the image of the rodent in the bottom left-hand corner. This can be particularly a problem when we have solar farms in the middle of a field, in a grassy field. If the cables are lying down inside the grass, rodents and small mammals, they do like to chew the cables. So do watch out for this. And also with these kind of arc faults and smoldering, you might have a sensation in your nose. You might be able to smell the arcing also. So what I would also like for you to check, as well as the panels, because although we're electrical people and we're going to do tests with the electronics of the system, we would be remiss not to also check out the mounting system. So are there any noticeable issues with it at all? Corrosion is a very big problem, particularly if we're in a high saline environment, say by the ocean. The salt in the atmosphere can really degrade aluminum systems, particularly if the layer of anodization has been corrupted or wasn't applied correctly to the metal itself. Similarly with stainless steel and galvanized steel systems, we can get oxidization, so it can rust if we break that protective layer. If you're dealing with a roof-mounted PV array, just check there are no cracks, particularly around the roof hooks, because that will cause water ingress into the roof. And if you're on a commercial roof, similarly, if you see any issues with the systems, any perforations that have been caused by the installer, my advice to you would be get off that roof straight away. Go downstairs, talk to the owner, tell them they have a problem with their roof. Because if they find out they have a problem after you've been on the roof, guess whose issue that is? That's yours. You caused the problem. They will blame you. So just be sure to check that there are no perforations inside the roof. Here's the picture I mentioned earlier. It's in the wrong order, so apologies for that. But this is the big JCB machine that was kicking up the stones and breaking the panels. But I think this particular slide really does highlight that if during your visual inspection you see that the panels are dirty, you really should clean them prior to testing. Okay, make sure that you clean them and that we're testing from a clean array. And there are some really good reasons for doing that. So what we can do is, by using the Seaward or the Solmetric range of test tools, we can test prior to the first cleaning session. So we test when they're dirty and we measure the result. And then we clean the modules thoroughly, and then we can test again. Now the difference between the before and the after cleaning, we can do this as a percentage. And then we can go to our clients and say, hey, Mr. and Mrs. Smith, I've cleaned your modules. This was the output I got prior to cleaning. This was the output I got after cleaning. This was 10, 20, 30%. This equates to this amount of cash and this amount of electricity generated. Therefore, why don't you buy a maintenance or cleaning contract from me? I will come out every couple of months and clean your panels, and you can see that the return on investment for that will be paid back instantaneously or very quickly, because you're losing 30% and I will charge you X. So we can put a very good financial case to our clients there for cleaning with this data. And again, this is the site in the Middle East that I mentioned earlier before we began testing. So you can see if we'd have tested when it was that dirty, our results just wouldn't have been very good at all. As you can probably tell from my accent, I'm originally from the United Kingdom, and I found that testing in my country of birth is quite difficult at times because the irradiance levels are very low, particularly in this time of year. So this was a site in Ludlow in the United Kingdom, and as you can see, I was asked to come out to test this site, and we had to call it off. The trip was wasted because we had below 100 watts per meter squared of irradiance. This picture was taken at about 1 o'clock in the afternoon. So really the sun should have been quite high and we should have had good irradiance. But sometimes geographically that's simply not the case. And what we really need to do with regard to this aspect of testing is manage the expectations of our clients. So if the client says, I want all the testing done in 3 months, you can say, okay, we can do 3 months, but with the caveat that we have good weather. Because if you have 1, 2 weeks, 3 weeks of really bad weather with low irradiance, you're not going to hit that 3-month deadline. So you need to be realistic in your maintenance contracts and manage the customer's expectations. So again, this is all our pre-testing. We haven't done any testing yet. So we've covered our PPE. We understand the difference between 1000 volt and 1500 volt systems. We've also done our visual inspection. But now it's probably time to mount our radiance meter and get ready to begin our testing. So we should make sure that this is in the same inclination and azimuth as the PV array that we're testing in order for us to get the most accurate results. Seaward Group, we offer a suction cup. This goes on the back of the solar panel and it's attached to it is a thermocouple, and this is where we get the cell temperature. Now this should be located away from the junction box of the panel, probably 6 cells down, 4 inside, away from the junction box, and junction boxes are placed differently on different panels, but we want a cell that's generally in the center of the panel. Similarly with the PV analyzer from Solmetric, ensure you use the clamp to get it onto the side of the panels correctly and securely. We don't want that thing falling off or anything like that during the testing process. So, as well as all of this pre-testing preparation we've already done, I mentioned that we should understand what kind of voltages and current ratings we are going to get from the system that we're going to test. And we can do this very easily using some simple maths. So for instance, for our string voltage, we can actually calculate what we should expect by taking the number of modules in the string and the STC VOC, multiply those two together. We can also multiply by the temperature coefficient, but this will give us what our expected open circuit voltage should be. So for instance, if each panel is 40 volts, we have 10 panels, we should have 400 volts, okay? And this is also affected by temperature, so we should also multiply by the temperature coefficient. For string current, we can do a very similar equation. So we take the STC short circuit current and we multiply by the irradiance factor. Now the irradiance factor is whatever irradiance you're measuring right now divided by STC, standard test condition irradiance, which is 1000 watts per meter squared. So if you're testing at 500 watts per meter squared, divided by 1000 times by the STC ISC, which for this instance, let's say 8, so that would be 4 amps. So when we do our test, we should see 4 amps. So with these figures in mind, before we've even begun testing, when we run the test, we can know if we're in line with what we expect. Now, if your measured values are not in line with your expected values, this could indicate a few different problems for us. So if the measured VOC is not in line with your expected VOC, this could mean that we have shorted bypass diodes, PID, wiring and connection issues, and that's the main problem. And particularly if you're commissioning a system and not maintaining a legacy system, reverse polarity. So maybe it's a Friday afternoon, the guys, they were trying to get away quickly, they put a positive on a negative, that's reverse polarity. That's causing us a real problem. Similarly, if your measured short circuit current is not in line with your expected short circuit current, this could mean we have ground faults, or the most popular one, or the most unpopular, but most prevalent I find, is micro cracks. And these are hairline cracks in the PV cells which cause shunt resistance. That energy has to go somewhere, it's released as heat, so you can also diagnose these with an IR camera. Or generally, if your ISC is low, it could be a combination of faults also. So don't think we're only going to have one fault on a PV array. So also we should be familiar with the software that we're going to use prior to getting on site. At Seaward we have a couple of options with regard to software, and I'm not going to cover these in any great detail, but also Solmetric have a very, very good software tool, the PV analyzer. These will generate STC curves, power curves, nominal curves. They will give us intelligent reporting on what the system thinks is wrong with the string. So I do advise before getting on site, familiarizing yourself with the software that you're going to use. Free training is available on all these software packages if you purchase your instruments from Seaward Solar. So, again, we've covered what PPE we should have, we've covered the visual inspection, we've covered the differences between 1500 volt and 1000 volt. We've also now understood how we can calculate what our expected values should be. Now we need a framework to actually do our testing process. And a very good one to look at, and I'm not going to labor too hard on this, I would advise making a note of this standard and going out and taking a look for it, is the IEC 62446 2016. So they give us an outline of how we should test and commission PV arrays of all sizes. So please do take a look at this standard, and this will give you an outline of what we should be looking for and testing too. Similarly, if you're in North America, we can look at the National Electric Code, Article 690.1. That has a lot of details. It also covers the rapid shutdown requirement for residential systems. It also covers DC optimizers and a lot of other things. It's very good. Not all states have adopted 690.1, but the majority have. But what I would say was I attended a conference earlier this year with UL, and they're looking to amalgamate, they're looking to put in line their standards with the IEC standard I just mentioned. So primarily I would look at the 62446 from the IEC. When we look at the IEC test categories, I've just noticed that I made a little bit of an error there with the title, so I do apologize. But we can see that the Category 1 tests and the Category 2 tests are split. So here is a list of which instruments we provide against which tests they can perform. And I'm going to cover each of these tests in a little bit of detail now. So first of all, we have earth continuity, and this is a very kind of standard electrical test, particularly in portable appliance testing and in the residential sector of electronics. So where the protective or bonding conductors are fitted on the DC side, such as the bonding of the array frame, an electrical continuity test shall be made on all of those conductors. The connection to the main ground terminal should also be verified. So basically what we're doing is we're ensuring that any leakage current has a path to ground. So no one's going to get a shock. We have a good grounding on the system. So with the PV150 and the PV210 and the 200, you can actually perform the RPE test. Again, the instrument is handheld. You press and hold the RPE button with the black and the red cables connected. And first of all, we null those cables. So if there's any excess resistance inside, we've nulled that to 0. And then it's very easy. We connect to the ground, and then we use a point-to-point method to test the earth continuity. So this could be to the frame, to the backsheet, to the combiner, and we're just making sure that the path to earth is consistent throughout the PV array. A bigger concern really is insulation resistance. Inadequate insulation not only increases the risk of electric shock, but it also reduces the overall performance of a PV system. And a portion of the DC power generated by the PV modules is lost via that leakage to earth. So insulation resistance is a very big concern. So when we're testing PV systems, a lot of people have their own standards, but the IEC standard says that we should look for 1 mega ohm of resistance at least. So again, very similar to the RPE method I described earlier, with the PV210 and the PV200, you can do a separate mega test, as they call it here in America, up to 1 kV, and we connect to the ground. We can do into the positive, into the negative, we can do the frame, and we're just making sure that the insulation resistance throughout the array is consistent and at a good level. The PV210 can also do this as part of an auto sequence where it will give a curve trace, insulation resistance at the same time, which is really useful if you're looking to save time on site. So this is a little bit of a bigger topic than just connecting at the end of the string. So most commonly in solar farms worldwide, we're dealing with a combiner box. Now, those unfamiliar with the concept, it's very simple. It's in the name, actually. Say we have many strings, or 20 strings, 30 strings perhaps. What we do is we combine them into fuses inside of a box. So in each of those fuses will either be a single string, or perhaps, as I mentioned earlier, several strings in parallel. So what we need to do as an engineer is we need to test each of those individual strings if we can. Now, what we don't want to do is test all of them at one time, because that means they'll all be in parallel and we'll have a very high current rating, and this will damage your machine. So we've devised a method which can very quickly and easily test inside of a combiner box. So first of all, safely open the combiner box and isolate the AC side of the array if you can. Select the correct voltage on your instrument and then insert all of the negative fuses if you have them. We also then want to connect to the common negative, okay, the common negative bar. We want to also open up all of the positive fuses, okay, so those are all open, and connect to the common positive bar. So the situation right now is we're connected to the negative and all of the strings in the combiner box are sharing that common negative, and we're also connected to the common positive, but all of the common fuses are open, so there is nothing flowing, okay? Now what we do is we insert one fuse, we push test. So that means we're testing one single string in that combiner box. We run the test, we save it, open the fuse, close the next fuse, test, save it, open the fuse, close the next fuse, test, save it. And this way we can quickly go down the combiner box and run through the whole combiner box. I think we maybe did a 30-string combiner box in about 13 to 15 minutes with a PV210, and similarly with a Solar Utility Pro. The PV analyzer from Solmetric is very quick also, giving us a good IV curve sweep. So that's a very quick method to be able to test in a PV combiner box. If you have any questions on this, please do feel free to email me, and I'm also available to come out to site and show you how to do this. String level testing is a lot easier than in a combiner box. You have a lot more confidence that you're only testing a single string, but do take a look down the string to see if you have any Y pieces which are connecting two strings into one, because that could cause an overcurrent situation. And also be careful when you're disconnecting and reconnecting the MC4s. Make sure you get a solid connection there and that there's no dirt or grit in between, or eventually that will cause arcing and insulation faults. All of these should really be a two-man process, so have someone with you to help. Follow all of the safety guidelines that you obviously did in the beginning prior to your visual inspection, and ensure you get a solid connection. And again, do not neglect your personal protection equipment. We cannot stress this enough. So a couple of tips for taking good measurements. Always take measurements from a clean array. I think I described earlier how important that is. We should also retake measurements with large deviations. So one of the biggest issues I find when I get PV data back from our clients is that they tell me, well, look at string number 17, I had a bad test. And then they go on to string 18, 19, 20. And I say, well, why didn't you retest 17? What if the clouds moved in the sky? What if someone walked in front of the panels? So if you see a bad result, if you look at your tester and you see that your measured results are not in line with your expected results, see if you can replicate that negative outcome. See if you can replicate that negative result. And if you replicate the same negative result 4 or 5 times, then you have a problem with the string. Not if you only get one negative result. I can't stress that enough, because if then you get back to the office, what's going to happen? Get out and test that string again. So make sure you do it while you're there. Save yourself time, save yourself hassle. We also need to ensure that the irradiance level is stable. So make sure that the clouds are not coming over regularly, that we're dipping from 900 to 600 to 800. We need a very stable irradiance level when we're testing, because this will make the current level very stable as well. Also let your temperature sensor acclimatize to the back of the panel. Don't just put it on and test. Okay, we're actually using a thermocouple, so that thermocouple needs time to acclimatize to the back of the panel. So when you're connecting the instrument, please ensure that you make a firm connection. I cannot stress that enough. Don't leave any gaps or between the inputs or the connectors, either in the instrument or with the cables themselves. Keep the device clean. I've been to many sites, and you saw the picture of the site in the middle of the desert. I've seen many site instruments that are very dirty. They get thrown in the back of the pickup truck. They're left out in the sun, stored at room temperature. Don't smoke around it. Treat it like the expensive test instrument it is. It's not a multimeter. Okay, these are very advanced pieces of test equipment, and we need to treat them correctly. So I would also recommend keeping some spare batteries on site because batteries do run out. You know, we're testing very large solar farms, so it's always good to not have to stop testing, not have to go back to the site office, get some more, then come back out. Always keep them with you. So, that first half of the presentation, we covered a lot about the practicalities of testing PV arrays. We covered the visual inspection, we covered personal protection equipment, and we covered how to make the connection and what we've seen in the field. Now what I would like to talk a little bit more about in the second half of this presentation is the IV curve and what the shape of the IV curve means. But prior to that, please let me explain the concept. So what we do with IV curve tracing is we short out the circuit inside of the instrument, then we vary a resistive load from short circuit current to open circuit voltage. And what we do is we take points along the way. Okay? And what this does is it gives us the characteristic IV curve, but it also gives us the max power point. And the max power point is shown on the IV curve. It's very useful to us. So this is how we generate the IV curve. Now I can tell you a few things we can do with it. So one of the first things we can do is to look at is the fill factor. Now, there's quite a complicated equation on the screen there, and I'm not going to get too bogged down in the scientific theory of IV curve tracing or fill factor, but I can explain this kind of in almost layman's terms. So if we have our IMP, so our current max power point, and our VMPP, our voltage max power point, this will give us the max power point. So this is where the system should be to operate at its maximum in our measurement. But also if we take short circuit current and open circuit voltage and we draw a line like this, so this is section B, this is our potential maximum. So we've got our measured box A versus the potential maximum. And the percentage that A fills B, that is our fill factor. And what the IEC standard tells us is we should have at least 60 to 70% of A filling B. So we're looking for a fill factor of above 70%. Okay, if we have a really low fill factor, this is indicating that something is really wrong. So on our instruments, all of the curve tracers we provide, there is a fill factor indicator. So after you run the test, double check the fill factor, make sure it's not really low, especially if your expected ISC and VOC are not in line with your expected value, if your measured VOC and ISC are not in line with your expected values. So what can we do with these curves? Well, you will notice that on solar PV data sheets, they actually do provide an IV curve for us. Now this is done in the factory, okay, and we have to understand that this is done in very tight regulated laboratory conditions. So they have a flash tester, everything is monitored, and admittedly this monitoring and standard does vary from factory to factory. A very cheaply produced panel will not be tested to the same standard as a very high quality panel. So do be aware of that when you make your choice in buying panels, that what it says on the data sheet is actually probably nowhere near what you're going to get. But what we can do is we can take our measured data, transpose it to standard test conditions. Now standard test conditions is 1000 watts per meter squared, 25 degrees Celsius. So if you're testing at 500 watts per meter squared, 12 degrees Celsius, we have to transpose that measured data using some clever algorithms, and that will generate our STC curve. And that's what our software can do for you. So when would you use IV curve tracing? Well, there are a couple of stages in the life cycle of a PV system when you can use it and when it's useful. One point is the pre-installation phase. So this is as the modules are coming off the back of the transport, you may want to just do a couple of curves on a couple of panels. I'm not telling you to do curves on every single panel before they're installed, but say you had a sample set of one panel in every 10 pallets. This would give you a good indication if there's any manufacturing fault with that batch. because generally when the pallets are kept together from the factory, they're not separated often. So if you can catch one bad panel in a batch, that might suggest that the rest of that pallet has the same manufacturing fault. We can also monitor the LID effect. LID is light-induced degradation. So you imagine the panels are made in China or here in America. They're flash tested, then they put in storage. Then they're kept in the dark for maybe months at a wholesaler, and then eventually they get taken off the truck and they get put on in the field. What happens is the sunlight hits those panels, agitates the panels, and that means the output is higher than what it normally will be. So that LID effect will reduce over time. So what we can do is we can test as soon as we put them on, and then test a couple of days later, and the drop in performance will be the noted LID effect. It also gives your clients peace of mind, particularly if it's on a smaller job. The client's watching over you, what you're doing. If you're testing a panel as they're coming off the delivery, and he sees that, he's going to think you're a very diligent installer and operator. A very good use for IV curve tracing, and probably the most popular out there in the PV world right now, is at the commissioning stage. So what we're doing is, to set the scene, the panels have come off the truck, all of the groundwork has been done, we've installed the panels, the combiner box has been fitted. So now we want to set a benchmark for all of our future tests. So what we do is we take a curve trace of that array and we set that, so that's year 0. And then when we come back to test the array in 2, 3, 4, 5 years time, or whatever the increment may be, we can compare our original IV curve to our current IV curve. And the difference between those two will give us the difference in the performance. And what this means in real terms is that we can go back to the module manufacturer and say, hey, listen, you told me I would have 90% generation after 5 years. I've done this test against my benchmark and I'm only getting 85% after 5 years. Therefore, Mr. Module Manufacturer, I would like to claim on my warranty. So IV curve tracing is a good way to set a benchmark for future testing and for future warranty claims. Ongoing O&M, operations and maintenance of PV plants, is a great concern. So even when the number of installations drops in your country, there will always be panels and installations that need to be tested and maintained. So IV curve tracing is the most powerful tool we have to diagnose issues. Whereas we can determine issues with VOC, ISC, insulation resistance, okay, open circuit voltage, short circuit current, insulation resistance, the IV curve gives us a bit more in-depth data. So my suggestion would be test VOC, ISC first, and if they don't line up with your expected values, then pull out the curve tracer. So you can quickly troubleshoot generation loss. You can test at a string level to find a problem at a modular level, and I'll describe how to do that for you in a second. And finally, with our instruments and the solmetric instruments, your engineer in the field can email a report back to the office while he's on site, very, very quickly. So I mentioned that the different shapes of the IV curve can tell us different things about the PV array. And so I would like to cover some of the main points in this aspect and of the shape. And the first is a reduced current. So this can mean a lot of issues with the PV system, but what I would first check is that you're getting correct irradiance data. Okay, make sure that you're not getting higher or lower than what you should be getting. So this goes back to us that we should have the irradiance meter in the same plane, in the same azimuth as the PV array. But potentially, we could also have earth leakage, micro cracks, or uniform shading. And if you haven't done your visual inspection and you test a string that is 200-300 feet down the way, you might not know that it's covered in dirt. And you think, oh, I have low current on my IV curve. Yes, because you didn't take a look and you didn't clean the panels. So this is vital. And also with micro cracks, as I mentioned earlier, this could be a path of increased resistance through the cell. You might want to just pull out your IR camera and take a look and see if you find any hot spots. A reduction in voltage normally means connection problems. So do be sure to check the connections during your visual inspection. But also on legacy systems, it could mean that we have PID. And as I mentioned earlier, this is going to become particularly prevalent in 1500 volt systems that are not secured for PID. So this is also true if you have a low voltage, but also a low fill factor. So a combination of a low fill factor, a low voltage, generally suggests that we have PID, particularly if the system has been installed for a long time. This is one of the most common curves that I see in the field, and this is the stepped or the notched curve. So basically, when we have multiple faults in a PV string, we will see it going up and down like this. This could potentially mean we have spotted shading. So bird droppings or leaves on the panels, so the current is flowing, it's hitting the shade, and that's slowing it down and causing a notch in the short circuit current. However, the most common cause of this type of stepped curve is microcracks. And microcracks are not just found on legacy systems, they can be on brand new systems. Maybe the truck driver, when he was bringing the panels to you, he was a little bit overzealous at the wheel and they were bashing around. Or perhaps your installer took the panels onto the into the field on his hat, on a hard hat, and that could cause cracks. It really does happen. So we need to ensure that our operators are handling the panels gently and with care. And the amount of times I have seen people standing on solar panels or putting a bag on solar panels, don't do that. It is not good practice. It will cause microcracks that you cannot see. So here I have a quick guide to IV curves. You can get a copy of this presentation, so there's no need to write all of these down. But whenever you go out testing, it's maybe good to have this either on your phone or printed in your bag, and then you can refer back to it and help you identify where the problems are. The final slide here, I mentioned earlier that we could detect problems at a modular level by testing at a string level using IV curve tracing. And I'm going to show you how we do that. So here's the scenario. You've connected to a string in the combiner box perhaps, and you've run your IV curve trace, and you have steps in the curve. So now you know that one or more modules in that string is at fault. So how do we then identify which individual modules are at fault? Well, traditionally what we would have to do is disconnect from the combiner and test each individual string. That's very time consuming. We're making connections and disconnections, perhaps adding further error to the array. So what we need to be able to do is keep that connection in the combiner at that string, but identify the individual panel. So what we do is, and this is why we work as a two-person operation, we take something that we can shade the panel with. So what we do is we go to the first module in the string and we shade it. That means the bypass diode in the panel will activate. So we're still completing the electrical circuit, but that panel, the PV cells in that panel have been isolated from the string. So what we're going to see is we're going to see a drop in power, okay, but the IV curve will still be the same. So what we need to do is shade, curve, shade, curve, shade, curve, until we shade a panel and our IV curve turns to its natural bent knee shape. What that means is we've identified the faulty panel by this selective shading method. So this is a very powerful tool for fault finding, particularly on 1500 volt strings where you have 30, 40 panels in a string. You don't want to have to disconnect each of those. So by perfecting this method, you can quickly and easily find out where your problem module is. So thank you very much for joining me today. Here are my contact details. Please feel free to get in touch with any questions. What I'm going to do now is I'm going to bring up the questions section and I'm going to answer a few of those. And please do feel free to answer any more questions that you may have saved up. So let's bring out the questions. So I have a question from Nick Lane. Nick says, what does RPE mean? And what are you talking about how to safely connect to the array? Well, first of all, RPE means continuity of Earth. Okay, and we did cover how to perform that. And when we safely connect to the PV system, what I'm saying is we don't want to connect to something that we're going to put an overcurrent through our instrument. We want to have the correct PPE. We want to make sure that we're having secure connections. We don't want to just do it haphazardly and think we're connected safely. Yatin Shnar asks, what should positive to ground and positive to ground voltage on a healthy array? To ground voltage. So when we're doing positive to ground and negative to ground, we're not measuring voltage, we're measuring insulation resistance. So we're measuring resistance, and that's actually in mega ohms. And the IEC 62446 standard tells us that should be at least one mega ohm. So I would advise going to take a look at that standard. Danny Farm says what the nominal IV curves is. He's mainly interested in how to correctly analyze the actual IV curve reading of solar modules versus the manufacturer's specs for warranty claims. Okay, so the STC calculation is different to the nominal. What we get from the manufacturer is STC values. Okay, that's what the manufacturer said all of their panels should be. Nominal values are actually a little bit more realistic. Okay, that's taken from another database called the Sandia database, where they do independent verification. So actually the nominal value is a lot more accurate than the STC value. Stephen Bale says, I've used the PV150 to test installations through a string. However, when the panels were covered in snow or shade, we get low readings. This is what's happening inside the string or the panels, or is this what is causing this low installation resistance value? I would really test when the panels are clean. Okay, that means no snow as well. It also could mean what I mentioned quite earlier in the presentation, is that we may have moisture in the connections and that's causing an insulation fault. So I would make sure that you're only testing insulation resistance on a clean, dry array. Okay? Can you take a moment to discuss troubleshooting on systems with DC optimizers, asks Sean Taylor. Sean, unfortunately, there's very little we can do to interact with DC optimizers. Once they're disconnected from the inverter, they only output a single volt. And this is part of the rapid shutdown requirement for residential systems. So there's not particularly too much we can do with our instruments to interact with DC optimizers. However, systems such as Solar Edge have very good diagnostic tools built in within their monitoring platform, so you can always check that. Or you could also disconnect each individual DC optimizer, connect in the tester, and test the panel bypassing the DC optimizer. Antonio Vega asks, why the software doesn't work on the iPad? Good question. When we were developing the system here at Seaward, the PV210, we found it a lot easier to develop for Android, a lot easier to get the software up onto the Google Play Store. So that's why the system is not on Apple. However, we do have plans for that in the future. And also Android devices are very cheap. You can pick one up for $50, $60 that will have near field communication and interact with our PV210 and 200. And also if you're using the Solmetric tools, that will only actually operate with a Windows platform. So I would advise a Windows tablet, perhaps a Surface, to interact with that. Eric Daniels asks, what is the accuracy of your field IV measurement? Very, very tough question, Eric. This varies greatly on the environmental factors. Our PV210, we say 10% from the MPP, but it really does make a big difference as to how the irradiance meter is mounted, how the temperature sensor is mounted, were there stable irradiance conditions. All of these things really do cause problems for IV curves. So I would say follow the best practices that I've outlined in the presentation. Mike asks, how often do the weather sensors need to be calibrated for the PV210? This really depends on use, but the instrument itself will tell you when it needs calibrated. It will come up with a message, cal. We normally say about 12 months of weekly usage. Considering a de-energized trackers, shall I reduce the testing? time only in the time window when I have optimal irradiance? Asked Marco. Yes, Marco, only test when you have optimal irradiance, particularly if you're testing similar strings within the same area. We want the same irradiance for all of those strings, then we can make a good comparison of our data. Chris Harris asks, snail trails, what effect do they have? Chris, they have the same effect that any shading would have on a panel. You know, particularly if you have a lot of snail trails or slugs, that's definitely going to cause hotspots. So make sure the panels are clean. Any type of shading is going to affect the current output. Let me see. A question from Yatin. Is it usually used as a quick check to find faults in cable when insulation resistant tester is not available? No, that's absolutely fine. You know, insulation resistance can tell us a lot. And normally if you have low insulation resistance, you also have a low short circuit current. Okay, question. Even if insulation resistance is less than 1 megohm, will the generation be still up and running? If yes, why? This really depends on the size of the string, I guess. But you will, as I just mentioned, insulation resistance and short circuit current, they go hand in hand. So if your insulation resistance is low, generally your short circuit current will be low as well, and that will cause losses of generation. Chris asks, is the app available in the UK? Absolutely, Chris. Get in touch. I can put you in touch with our UK team. Roger Williams asks, is there a minimum irradiance as per the 62446 for doing IV curves for performance verifications? The IEC 62446 tells us we should have at least 700 to 800 watts per meter squared of irradiance. I've seen decent curves as low as 400, but I think the higher the better. And the other reason for that is we're going to transpose that measured data to STC. So if we transpose it from 400 to 1000, the margin of error in our extrapolation to STC is going to be greater than if we go from 800 to 1000. So that the better the irradiance, the better, and also stable irradiance. I can't say how much stable irradiance is key. Christopher says, what is the industry standard Pmax measurement threshold as a percentage deviation from the manufacturer's specifications as it considered a PV string as a pass string during commissioning? Christopher, that's another great question, and one that the industry doesn't have a standard for. It depends on what each manufacturer of panels specifies, and it also depends on what your client will accept. So some will expect a greater margin than others. But I believe, and please don't quote me on this, please do check the standard, I believe 10% is a sweet spot, but you'd have to double check. Yatin asks, we've covered that one. Let me see. We've covered that one. I think that's all of the questions. I hope you found today's session very useful. If you have any feedback for me, I'd be very much pleased to hear it. You can see my contact details on the screen now. And I would just like to thank all of you for your time today. I would like to thank you for joining us. And please do note that Seaward Solar and Seaward Group USA, we have 1000 and 1500 volt test solutions available, string checkers, curve tracers, irradiance meters. Please do get in touch.